Alright, welcome back to another Learn PowerShell video. In this video, we're going to be covering day 7 of Advent of Code. This one was a fun one for me because I always talk about how important math is when you're scripting, no matter what you're really doing. You're always going to be using numbering, positions, and space, time, time complexity, all sorts of things. So this one kind of really I found awesome because it used something that I just learned about a few months back, about 4 or 5 months ago, and that's Gauss Summation. So what this is, and I'm just going to explain it quickly, is this kid, I think Thomas Gauss, something like that, he actually was asked in, it's Johann Carl Friedrich Gauss. He was this kid who was in class, and his teacher asked him to count up if you added all the numbers from 1 to 100 together, what would be your sum? And he very quickly answered, 5,050. And he had a very simple way of figuring out how to do that. So when we get to the second part of the problem, I will show you guys that, and I will also put a link in the description to the Gauss summation because it is such a simple solution, and I want you guys to understand it better. So without anything further, let's jump right in and look at the problem for today. So the problem for today is that giant whale has decided your submarine is its next meal. You got to get to this cave. There are crab submarines that are going to help you. However, the only way that they can bust through to get to this cave is if they're all lined up. And they can only move horizontally. They cannot move vertically, so they can only move on the x-axis. And they all have to be lined up completely. So we need to figure out the fastest possible way for them to all get lined up so we can get in there. So what this is going to look like is you've got all these crabs in different positions on the horizontal plane. Like this one is 16 over, this one happens to be at 0, this one's at 2, 7, they're all over the place. And we need to figure out within the least amount of moves, because we want to 1 for speed, and 2 because each move takes a unit of fuel, and these crabs are apparently in submarines. So we want to also reserve as much fuel as possible. Mainly just the shortest amount of moves, because speed, we don't want to get eaten by this whale. So this is a very simple problem because you just need to figure out if you move every number by something, you need to figure out how many moves that's going to take, and then you need to figure out what is actually the shortest amount of moves through all of that. So this was a problem that I immediately knew I would probably have to brute force, and I did exactly that. And I looked at a lot of the solutions online afterwards because I felt like maybe mine wasn't the most efficient or delicate. And it probably wasn't the most delicate, but it actually turned out to be fairly efficient. It only takes about 2 seconds to run. And I thought that I was going to really just hardcore have to brute force it and just guess every number, and I thought my code might take forever to run. The code doesn't actually take forever to run. As I mentioned, it only takes about 2 seconds. So I'm going to walk you guys through this. So let's pull in the puzzle. And what we have here, if we look at the puzzle, we've got all sorts of crabs in all sorts of positions. Now, from this, we only need to know 2 things. 1, what the crab is in the lowest numbered position, and what the crab is in the highest numbered position, because that's going to give us our number range on where they can move. They can't move outside of that because that forces every crab to move, which obviously can't be the most efficient answer. Even if every crab has to move, the crab at 0 doesn't have to move 1,900 spaces, if that's the highest, to get past the other one. The ones where they have to move the least amount of spaces, if we can have one crab move 1 and all the other crabs move 2 or 3 instead of all the crabs moving 17, we're in a much better spot. So all we need to do is sort them. But if we look at this puzzle input, we have a quick issue. So if we do puzzle 0 dot, oops, not O, 0, get type. This is a string. I can't use a string to figure out if it's greater than or less than something else. I could try to sort, but if you sort a string, then it goes 0 and then 1, and before you hit 2 actually, it actually sees 10 and 15 as lower values in a string than 2. It holds 2 as a higher thing because it comes further down in the character string. Anyways, a string is not the same as an integer, so just because you think it should be applied in your head, just don't always think that the computer does that, because it's not always how things work. There's hard-coded logic to handle these things. So we're just going to overwrite puzzle by saying that puzzle is, for every object in puzzle, we want to have that puzzle as an integer. And then, sorry, I had a notification pop up. We want to sort that whole object after we have them all as integers. So that then looks like this. We have a nice, pretty array of all of our items, and everything is clean, all the way up to 0, which is fantastic. What we could do, and this is what I did the first time I did this problem, is figured out what the midway point was, and then figured out how many numbers were lower than the midpoint, and then how many numbers were higher than the midpoint, and I brute force from there, because if there's more numbers on the lower end of the scale, below the midpoint, then our answer is most likely going to be on that lower end of the scale. So I divided it in half, and then I divided it in half again to figure out if where my starting point was. If I was low or I was high, just by using the same formula, but then only plugging in one number, because again, I thought this was going to take a lot longer to run than it did. Why I'm explaining that is because we're actually going to use my guesstimation as our starting point, at least to figure out kind of what we need to be lower than. So as you guys remember, we can just do puzzle 0 and -1 to get the lowest and highest amounts in small and large, if I put an equal sign here. And so for small, as you guys saw, we have 0, and large should be 1855, because we see that that's the last number, 1855. Perfect. So again, I mentioned that I took a wild guess using this formula as the number that I wanted to use to start for the position that everything needed to be in. So what I did was said that our mid equaled our large divided by 2. And I think I got like 967 is what it is, something like that. Yeah, 927. And then I did that again. So then I said mid equals mid divided by 2, and this is like 463. There we go, 463.75. And then I ran only this one number against all of the crabs to figure out if I was high or low. Obviously, you can't be low. You can only be high. It just depends on how high you are. If we were low, then there's a lower number of moves than we could possibly ever be again. But if I was too high, then I knew that my guess was wildly off. And if I was pretty close in like a guess, then I know I'm on the right track. And my initial guess was that 500,000 was probably somewhere about what I was looking at. And this was just a guess because everything has to move, and I had no idea where my point was. So using that one number, I plugged it in, and I got my attempt number at the final result was 360,000, which is like 362,560, and if I want, I can write that exact thing, 560. and start there. So what we're going to do is we're going to say for each number in small to large, and that's 0 to 1855, then we're going to run our code against that. So first thing we need to do is say that our fuel consumed is 0. And why we need to do this is because for every single number in this, we want to try again to figure out what our consumed fuel total is going to be, and we can't do that if we're just adding to what we have. So we need to reset this to 0 and try again and figure out where we're at. But with that, we also need to make sure that we're saving what was in this fuel consumed so we know if we're doing better or worse than we did before. So we can say if fuel consumed is less than our attempt number, then our attempt number becomes the fuel consumed, and I want to save what the position is. Position equals n. I want to figure out where they all had to align. This is not part of the problem, but I was curious. So I want to see where the position was to make them all line up that was the lowest number of moves that caused them to move so many moves. So what we're going to do now is say for each crab in the puzzle, we are going to say that our fuel consumed equals our fuel consumed from the previous run. To start, it's going to be 0. Plus, and this is something you guys haven't seen before, math, and we need an absolute number. So what's going to happen is that sometimes this number will be negative. So if our crab is in position 0 and n happens to be on, let's say 4, or even 837, that's going to yield a negative result. I don't want a negative number because I only need to know how many positions it had to move to get to this spot. So it's always going to be, for me, a positive number because it's just the number of positions the crab had to move. So you have to do this absolute call to make sure that your number is always a positive number. You could write some crazy logic like that if this number comes out to be lower than 0, multiply it by itself, but that's wasteful when you already have this math class that you can use and call the absolute function inside of that. So from here, we can really run this and just figure out what that is. So let's just say that our attempt, let's print that out, and position. So let's run all of this. And this is the right answer, and the position that they would all be in is position 321 using my puzzle. Now, this is awesome. It only takes a few seconds to run, but I was curious how long this actually did take to run because I just had that other puzzle for 6 that took 50-something minutes, and that was really irritating to me. So something else I haven't showed yet is measure command. And you can do this on anything that exists. You just wrap whatever you're trying to test in curly brackets and run measure command. Let's reset all of this. And this took 2.9 seconds. That's fairly fast. How do we make this faster though? Well, there's one way to do it. We can say that if after doing this math, after adding fuel consumed to itself, if that happens to be bigger than our attempt, we don't need to keep adding the rest of the numbers or the rest of the fuel that comes in after that. So let's say in some cases, we might hit 7 or 8 numbers into our run, and we've already exceeded this fuel consumed, this attempt. So we just need to get out. So if fuel consumed is greater than our starting attempt, then we want to break. And now let's measure this using this 2.9 seconds as a baseline. And as you can see, running all of that all over again, it took 0.008. That is incredibly fast. It is a lot faster than the 2 point whatever seconds that it just took, 2.9 seconds. So this is an incredible way to get out of something if you're already done. And all this is going to do is break this for each. Oh, whoops, actually, that's in the worst spot possible. Actually, I guess... No, so, okay. So the place that I just put it in is perfectly fine. So I do apologize. This is the best spot for it because this is going to break out of this for each and then go right back into the next number in. So I do apologize. Didn't mean to scare you. This is perfect. So this is just going to say that every time we're in this loop, if we happen to break over this fuel consumed over this attempt, then get out of this for each and go into the next number for this one. You can, if you wanted to use continue, what would happen is it will actually stay in this for each. It will just move on to the next number. I don't want to do that. I want to get out of this completely and just move on to the next n, because the next number here is still going to exceed it because I've already exceeded it like crazy. So there you go. This is the way to get the code running the absolute fastest and the most efficient way possible. And I will cover time complexity in a video very soon talking about big O notation. But let's go take a look at part 2 and see what we're dealing with. So in part 2, the fuel being used is actually more than we thought it was. So the first step that a crab moves only costs 1 fuel, but the second step costs 2 fuel, and the third step costs 3. And so seeing this, I immediately looked at this and said, okay, you're counting all the numbers from 1 to 5, and you're adding them to get 10 fuel, which is Gauss summation. So I will pull this up on another window, and we can cover this. Okay, so here we have Gauss summation, and if we added all the numbers from 1 to 10, we would get this answer 55. And if you look at this, so the result is always going to be the same, adding the first and last number together. So 1 plus 10, 2 plus 9, all of these equal 11, no matter how you look at it. So if you add 11 times itself 5 times, you get 55. However, this is not the simplest way to write this. So if we come down here, we can see that the total number of pairs times the sum of each pair, which is n times, n plus 1 times n divided by 2. So right here, Gauss summation. So n plus 1 multiplied by n. So the total number of pairs times the sum of each pair divided by 2. And you can see that right here. So the sum of each pair right here equals 11. So it's just the last number plus the first number, and it's 1 plus whatever. That's 11. That's the sum of each pair. And the total number of pairs is going to be the total number of numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So n plus 1 times n divided by 2 gives you the number. So from 1 to 100, you can see that the answer is not, oh, right here, 50-50, which is a very simple way to look at this, and this is the easiest way to look at this problem. So let's jump back over to VS Code and figure out how to code this. So I'm going to copy in a couple things just to save us some time. Let's just copy all of this and paste it again. I could do a function here, but my math problem is going to change, so a function probably wouldn't be the best way to approach this unless I wanted to plug in. I had two different math functions, or say which math function to use and have them both inside of the function. We're not going to do that. So what we're going to do is we're going to take this out completely because I don't want it to be there. And we're going to now say that we're going to use Gauss summation because I think this is awesome to be able to use something, a math algorithm that already exists that we can use. So we're going to say that our Gauss number is, or our Gauss n is what we already established. Whoops, I didn't mean to. And we're just going to do the same problem that we had before. So this is our n, and we're going to add 1 to that because I just want to do the n plus 1 at the start, because n plus 1 times n times n, and then divided by 2. So this is the problem, but that's not the Gauss number. So this is too much. So what we need to do is just back down to just what the n is, because we're going to add everything else in later. So let's, oh whoops, I did too much here, that's what I did. So ABS C minus n, that is our Gauss number. So what we need to do here is just write out the formula. So we're going to say 1 plus, I deleted the variable, Gauss n times the Gauss n divided by 2. So this is n plus 1 times n divided by 2, adding that to the fuel consumed. So real quick, let's go back to Advent of Code and check out what my answer was, so we can verify here in a second. So answer happened to be 92,439,766, which you can see right here. So let's tab back over to VS Code now and run this after we reload. Let's change our attempt to 100 million. And run this now. Let's also put the attempt, I should have just copied it, oh I deleted over it, and position. So our answer, 92 million, so just verified that with Advent of Code. This is correct. And if we wanted to, we could look at other ways to try to make this faster, like changing continue to break and running this again after we reset everything. And so that probably took about half the time. I can check again by using measure object. So let's just select all this, put it in brackets, and then say measure command, sorry, not measure object. Check what running it with continue looks like. 6.2 seconds, and let's change this to break. .8 seconds. Let me reload this just for fairness to say that we're starting from scratch again. .9 seconds. So it's still much faster, less than half the time was used, because we know that if we need to get out, we can get out and move on to the next iteration. We don't need to keep going and wasting our time. As soon as we break above that, we're just going to move on. So again, using this is a very quick and easy way to make our code lightweight, and an awesome way to just get out of things when we don't need to keep doing things and stop wasting our own time. This solution was incredibly fun to work on, especially once I realized that I could use this. And I encourage you guys to go look at math problems and figure out how to write them in code, math proofs or algorithms, and figure out how to write them, because I promise they will be useful at some point in time, just like this happened to be for me. So thank you, and I'll see you guys tomorrow for day 8.